Okay, what I'd like to do today is talk about systems of differential equations and where systems come from. So, back in Calc 2 or Calc 3, we talked about parametric equations, and this is really where systems are coming from. So, for example, we learned if you have some kind of curve in the plane, in the xy plane, right, that you can parameterize this curve. This might be at t equals 0, then t equals 1, t equals 2, t equals 3, t equals 4, t equals 5, and so on. And so this curve can be built. I'll use our Calc 3 notation here with our brackets as x of t, y of t. Good. And so we learned that a curve in the plane can be defined by a set of parametric equations: x equals f of t, y equals g of t. So rather than using the bracket notation, we'll go ahead and use this more standard notation. This is called vector notation. Vector is just going to be, for us, just a column with some elements in it. And so we'll have our x of t and our y of t as our two entries. Maybe I'll write that a little bit better. So we have a vector with x of t and y of t. Okay, and we're going to call that vector x of t. Good. Now we remember from our, I'm using x in two different contexts, but I think you see the difference there. This is the vector, this is a vector, and these are the components of the vector. We also know how to differentiate a set of parametric equations, right? And that is, you just differentiate piece by piece. So for example, if x of t was equal to t squared plus 3t cosine t, right, we could differentiate that piece by piece, 2t plus 3 minus the sine of t. Good. So if we can integrate that way, we can also anti-differentiate that way. So you can also integrate. So that would be the integral of t squared plus 3t, the integral of cosine of t. Right, so you would have 1/3 t cubed plus 3/2 t squared plus c, and then sine of t plus c1 plus c2. Good. Okay, and so on. I didn't want to get too carried away there, but good. All right. So because we have two expressions for x and y, we can, when we're looking at the derivative, right, you're going to have two equations in t. And so that's the important piece of this. So let me pause here for a second and set up another problem for us to think about. So we're going to go backwards before we go forwards and talk about, suppose that I have a system of equations: x of t equals cosine of t, sine of t. Right, then if I differentiate, right, that's going to be minus the sine of t and cosine of t. Right, well, if this is also xy, right, then the derivative of our system is minus the sine, which is minus y, and then cosine is minus x. Oop, not minus x, just x. And so what we could write, bringing these two together here, we can say that x prime is equal to minus y, and y prime is equal to x. And so these together form a system of differential equations. And we also see, by the way, that the solution is x of t equals cosine of t, y of t, equals the sine of t. And usually you want to present that as a parametric set, right? They go together. Good. Now, suppose I've got something more complicated. Let me pause for a second and set it up. Suppose that I've got x prime is something like x plus 3y and y prime equals, let's say x, just maybe x minus y. Good. Now, it is possible, by the way, for these to have like a plus cosine of t or something, plus t squared or something. We're just going to be basically looking at autonomous systems, and so this is a autonomous system. Okay, so we won't have t as an explicit function in ours, although we could. What I'm thinking about is I think I can, because I have a system of two equations and two unknowns, I think I'm going to be able to rewrite this as a second order differential equation. And the way I'm going to do that is I can take one equation, the first equation, and I could solve, why is my screen going back and forth? Solve equation 1 for y, right? So that would be 3y is equal to x prime minus x, then divide by 3, right? And then remember that I've got y prime is equal to x minus y in the second equation. And so what that means is I can substitute this in for y here and in for y here, and then I would have a differential equation all in terms of x. So that would be x double prime over 3 minus x prime over 3 equals x minus x prime over 3 minus x over 3. Good. And then just to clean that up a little bit, let's just multiply 3 by 3. X double prime minus x prime equals 3x minus x prime minus x. Good. And now we can continue to simplify a little bit. Yep, it looks like the x primes cancel, right? And we're going to 3x minus x is going to be 2x. So let's bring that over. That's just x double prime minus 2x equals 0. And so we were able to go from a system of differential equations, a first order, to a second order differential equation, and now we know how to solve that, right? How would you solve this differential equation for x? Well, the characteristic equation is r squared minus 2 equals 0, so r is equal to plus or minus square root of 2. That's kind of those are not nice numbers, but I just made this up off the top of my head. Sorry about that. X is c1 e to the square root of t 2t plus c2 e to the minus square root of 2t. Right? Once you have x, can we solve for y? Sure. Because once you have x, you can substitute it into this expression. Oops. Oop. You can substitute it into this expression for your y. Good. So these numbers are kind of messy, but we could do it if we wanted to. All right. By the way, if you had solved the second equation for x, would you get the same thing for y, so the same equation? Let's see if we could do that. We have about another minute. So, where should I do that? Hang on one sec, I'll just copy this over. Okay, so we could have used equation 2 and solve this for x, right? Because x would be y prime plus y. And then we could have plugged this into the first equation. So this would be, plug this in to both sides. What I'm thinking of is we're going to plug it into x prime and into x, right? So if we do that, we get y double prime plus y prime is equal to x, which is y prime plus y, plus 3y good. And so what do we get here? It looks like we're getting a different answer, huh? Y double prime minus 4y equals 0. Did we make a boo-boo up here? Oops, I think we did. I see it right here. Sorry about that. We should have put parentheses around that. And so that would have made this a plus, and that would have made this a plus 4. And then I would have had nicer numbers. Gosh, that would have been, I should have just done it that way. Okay. So now we have plus or minus 2t. Good. And so here then you would see that y is equal to c1, maybe I should say c3 e to the 2t plus c4 e to the minus 2t. Because it looks like right here, right, that these two things are the same solution, but they're actually not. They're going to be different linear combinations of e to the 2t and e to the minus 2t. Okay, so that's what's going to set them apart. Okay, I'm glad we fixed that. I think we'll stop here and start in the next video about how to do the conversion back.